Okay, this is a bit of switch from the melt systems off to the thermal conditions here. Tracy was intending to come, but actually she is in field camp at the moment. So quite a few of you have noticed Enceladus was kind of a surprise in a small package. It is itty bitty. And we would have expected this to be a fairly cool satellite given its size. Clearly that is not the case, much to our glee. 2005, evaporation of this relatively warm ice probably generates a cloud of water vapor detected above Enceladus' south poles by several other competing instruments. We've refined this a bit since then and seen plumes, but you can see the hot spot down at the South Pole. That should have been one of the coldest spots on the planet, and it is clearly the hottest one. So what gives? A few reminders. I know most of you know this, but just to make sure that we're all on the same page. The intensity of the plume varies with the moon's orbital position. We presume that the tidal mechanism is driving the activity because the cracks cycle through compressive shear and tensile stress regimes, as we've seen at least twice today, I believe, every orbital period. The global subcrustal ocean was proposed. The thermal budgets suggest that that may be quite difficult to maintain over a long geologic period, so perhaps it's just a regional ocean. That's somewhat supported by the topographic depression around the South Pole that surrounds the Tiger Stripe area. It is much more easily to maintain that smaller regional ocean with tidal heating with the huge budget for such a small body. So of course, this is the fun part. So we've got geysers or plumes. Just out of curiosity, show of hands vote, who prefers a plume? Who prefers a geyser? All right, plumes it is today. All right. Plumes, ignore that. Yes. We've got 101 jets detected. 100 of those are located on the cracks. The last one has a somewhat uncertain location, so we're going to just sort of drop that off the data list for the moment. So we've got plumes on cracks. And we've got an apparent jet structure, as Candy noted earlier, with both particles and with water vapor. You see the jets mostly in the particles, right? Is that right?
The jets, there are ice particle jets. There are also collimated gas jets.
Right. So we've got a little bit of a dual process going on there. I have heard it suggested that from the viewing angle, some of the things may look like jets that are actually part of a long curtain that is folded back on itself. Bends. There's some small bends in the Tiger Stripes. It could give you the visual appearance of a jet when in fact you've simply got almost like a double concentration of things being ejected out of a crack. So keep that in mind. They may not be as collimated as we think they are. And again, we've got the 4 major Tiger Stripes of Alexandria, Baghdad, Cairo, and Damascus. I simply reversed this here. Some people can see this a little bit more easily in the reverse. Okay, so they're all originating down here in the South Polar terrain. There's kind of a polygonal area that they're contained in. That's a depression, what would naturally suggest a locally thinner crust. Porco's 2014 paper maintains that you can get a water-filled crack stretching from a source to the near surface through the entire icy shell. It would be at least theoretically possible. I think several other people have suggested that since then. And again, as we just mentioned, while we certainly probably do have some isolated jet locations, the extended curtain eruptions could appear as jets. Okay, so what immediately comes to mind is this an example of heat pipe volcanism like we see on Io, or we may have seen on early Earth? And that means simply that most of the planetary heat loss is at a couple of very localized locations, in contrast to what you see on Earth, where it's all along plate tectonic boundaries. And if so, what can we say about the thermal budget of the planet and how fast it can be losing heat, and what does that do to the local tectonics in and around the heat pipe area? Okay, what's a heat pipe? It is not this. Just in case you're not sure. It's a conduit, simply, that takes heat and material from the base of the lithosphere up to the surface and lets it go, right? We love it. We're going to set it free. IO transfers roughly 40 times Earth's heat flux from the interior of the surface through volcanism. This is a very, very efficient mechanism. It's called the heat pipe mode because you've got localized channels, i.e. a pipe, and the melt simply carries the heat with it to the surface. In a heat pipe region, the repeated passage gives you a local thermal and structural weakness, a really profound one, orders of magnitude. And this in itself gives you additional eruptions that are favored to the same plumbing or crack system. This tends to leave the more distant crustal areas that are not involved in the heat pipe relatively cold and thick. And so that makes it much more difficult to set up another heat pipe somewhere else. And so this particular mechanism tends to promote very long-term eruptive centers. You don't have plate tectonics to move things around and disrupt those. And so you can have a thin cold crust remote from the heat pipe area. So I kind of like this quote by Moore and Webb in 2013, when heat pipe becomes the dominant heat transport mechanism of a planet, the effects on the lithosphere are both surprising and profound. This is an example of their numeric model showing an early Earth heat pipe setup in nature. And just looking at this here, these are heat pipes. And you've got extraction of the material going up where you're essentially advecting heat up to the surface. And then you've got downwelling as you take the cold material back down to the bottom for another load. We have this gorgeous thermal infrared data. This is Damascus Sulcus, and this nice high-resolution background image from the Cassini high-resolution imaging camera. You can see the crack there. You can see the composite infrared spectrometer data here, showing right down the crack. Temperature is 190 K or so within those particular pixels, and colder temperatures at the sides. Right? This is a really localized hot spot, if you would. If you look at what kind of morphology of the terrain you've got, the tiger stripes or rifts typically 130 kilometers long or so, a couple of kilometers wide. They've got a central trough here. Depending on which paper you want to look at, anywhere from 200 to 500 meters deep. They're flanked by these ridges out here, tens of meters high, occasionally 100 meter tall, again, depending on which paper you're looking at. And the spacings between the major troughs then are about 35 kilometers. Obviously, that's not exactly linear, so we're going to approximate that as a 35 kilometer spacing. All right. I love this. Doesn't it look like it's going somewhere? All right. So these regional background thermal structures, the heat pipes, they're clearly going to have some kind of effect on the local thermal structure. We want to model that. This is the cartoon I started with, where I said, all right, we've got some kind of regional ocean down here. We've got a rocky core. This is actually that background image of the plumes earlier, but the cracks are set at a 35 kilometer spacing. We've got 4 of those. The temperature you pick for the thermal equilibrium can vary a bit. It actually has very little impact on the results. It says 68 K here. I believe I used 75 Kelvin later. I'm assuming a narrow crack of about 1 meter. And we're assuming that this layer down here is essentially at 273 K. Okay. I'm ignoring completely the actual mechanism of the jet eruption, which is like the top few kilometers where things start to vaporize and leave, just because the impact on the regional thermal budget for that is actually fairly small. Curvature does have an effect. After running a couple dozen models, I realized that the effect was actually running about less than 5%. We have far more play in parameter space than that, so I threw out curvature at the moment, even though it looked prettier. Oh well. Okay, so we've got other internal thermal modes for the area. Abramov and Spencer, 2009, did one where they looked at the top 10 kilometers rather than the top 40. Most of them tend to focus on the near surface, obviously, because that's where we have the data. Insulation on the bottom for this particular model, and on the right, 273-degree crack, same as we've used here. Radiation at 75 Kelvin at the top, which I matched simply to check results. Okay. They used a linearized finite element method, and you can see kind of the result of that here. You get very straight curves, almost but not quite linear. Okay, so this is the dimensions I've got. These are actually fairly easily changed, so if you have a quibble with this, give me 5 minutes, we'll fix that. We've got a 40-kilometer crustal thickness over here. I took the last 50 kilometers away from the tiger spikes just so we could get the far field effects. We've got 35 kilometers in between each crack, and I put a symmetry plane in here, assuming that the solution on this side should be the solution on that side, just to reduce the computational time, which turned out to be a completely useless exercise because the whole thing converges in about 2 minutes. Oh well. Model flattened. Okay, again, I got rid of the curvature because we've only got a few percent difference down here. Here's our boundary conditions. We're radiating to an ambient equilibrium of 75 Kelvin. Again, the symmetry plane and cracks are there for reference. We've got a constant temperature on the bottom, just assuming that that is a molten layer of water down there. And insulation on the ends, meaning that we're going off to essentially infinity. I am using COMSOL multiphysics software. I've been using it for about 20 years now. This is an embarrassment of computational power at this point. It has gotten so good that what used to take several days on the Cray now takes less than 5 minutes on my laptop. We really don't have an excuse to be using a lot of analytic models at this point. It's pretty easy to run. You can throw in complex geometry, boundary conditions, space and time dependencies. You can add convective elements like a moving fluid in the heat pipe. You can change the phases. I've just started with the thermal conduction here because I do think we have a little bit more play in the parameter space than we have certainty on the parameters right now. The obvious drawback is that it's not cheap. I'd like to acknowledge University of Buffalo for letting me use their academic rate. And there is a bit of a learning curve. Okay. All right, so here is one of numerous very similar thermal model results. We've got the temperature scale in Kelvin over here. The heat pipes then are these bright white areas. Sorry, somehow in the translation to the PC, it added all sorts of little lines that really aren't there. Don't believe your eyes. So the white pipes then are the heat pipes, because those are the hot bits. We've got insulation down here. Well, actually, it's a constant temperature. It's 273 down here. So again, that's white. Over here, going off to infinity, you can see that the curves have essentially flattened out. So that should be a constant layer, mechanical and thermal thickness of the crust. And then right here at each crack, then you get the very hot material emerging. And again, this model kind of completely ignores the jet effect. So I would not trust, this as a prediction for what you see on the surface, other than, yes, it'll be hot. And it will be hot in a very, very narrow region. Now, the effect of putting the cracks together like this and putting them all in one model then is you can see that there is a general regional warming that could go a long ways toward explaining that topographic expression around the South Pole. Okay, before we go down the rabbit hole, you can play with these a lot and do all kinds of model runs with a lot of computational power with not enough constraints, which isn't very helpful. So what we need as additional boundary conditions, which I think a few of you have at this point actually, is a stress state timing function, which is essentially a periodic thermal boundary condition. How long is the vent open that we can have liquid running through that. And then we can set that up as a periodic boundary condition on here and see how the thermal response changes. Okay. If we've got that, then we can calculate the time-dependent thermal field fairly easily. And we can probably wrap that back in to iterate to a mechanical lithosphere and maybe get a gravity topography response out of that in order to predict what kind of topographic depression we should be seeing. And then at that point, it's adding curvature back in because that will make a difference there. So if we iterate through that a few times between the stress field and the thermal calculation, I do think we can get predictions for these things here. It did look sort of like a theater curtain. That structure was pretty robust no matter what boundary conditions I put in it. The temperatures scale a little bit when you fiddle with them, but the actual structure of the thermal solution really changes very little. So what do we get out of this? Well, it's hard to emphasize this one too much. The crack cryovolcanism heat transfer are very, very efficient. They will take massive amounts of heat from the interior, dump it to the exterior. Several cracks together, both thermally and by inference mechanically, are going to give you a thinner regional crust that will interplay off of each other very nicely. And the surface temperatures away from the cracks in between them should be quite cold. They will be very difficult to tell from the far field boundary conditions. The wall warming that you get from this along the pipes going up is likely sufficient to maintain each of these crack locales as a thermomechanical weak zone. And these will be strongly preferential paths for subsequent cracking and material sand. And in fact, I think it will be very, very difficult to move the crack location very far from those areas because they're going to be so weak. Even if the plume material tends to close the cracks up in those upper few kilometers, the thermal effect on the strength of the material should be highly conducive to that crack location staying essentially in the same location, maybe slifting around slightly because you've got some play there in how wide that area is. And those slight shifts may give you some lineated terrain effects. Okay, thank you.
There was some work done, I forget who did it, some time ago that suggested that even Earth's polar ice sheets are on the verge of sluggish thermal convection, solid state convection, and that there may be some manifestations of that convection in the structure. And so we're talking about a layer that's comparable to an ice sheet. And with this kind of thermal structure, it seems like solid state convection is going to be an added component to the complex. And then throw in Christine McCarthy's little bit of melt in the ice, and you've got lots of impurities to work with. We know that from the plume composition. It's going to be a messy system. So this brings up the whole idea of the toy results that we heard about this morning. I think it's all toy results, but really fascinating toys. We need another mission.
I will never turn down another mission. I agree that the solid state convection will definitely add to the heat pipe effect, but I do think that we now have enough parameter constraints from the last mission to put some more or less real numbers on how large we expect to be and what we've got for at least a thermal crustal thickness down in that area. Beyond that, more data?
Thanks for the nice presentation. I was curious, the heat pipes are imposed or do they evolve due to a feedback?
This is a time-dependent model. You can let them evolve. So I'm showing you essentially the end state of a time-dependent model, but you've got to start them somehow. So I started, I think I started this one with a heat pipe that went halfway up that was like 100 degrees warmer than the background and
so
let it go.
And so you model them by imposing?
I imposed essentially a start crack.
And then
However,
along that crack, you supply a heat flux, or you,
you don't have-
specify a
just-
temperature?
hold it at the temperature and it will warm.
Obviously.
But oddly enough, the end state looks identical. Once you've got that crack in place, it doesn't really matter how it got there. The thermal state is indistinguishable.
All right. My understanding is that the gravity data doesn't constrain very well the thickness of the ice shell in the South Polar region. And in your model, I think you're using 40 kilometers. And it seems that every time I come to a workshop, people are pushing it thinner and thinner. I've kind of stuck at about 10 kilometers because I think the float line then is around a kilometer of depth. And I think that I remember John Spencer saying that there's no indication of a liquid within a kilometer of the surface. And I guess he based that off thermal.
I think that's a good question, actually. I have not run it thinner than 10. And at 10, you still have a fairly profound cold lid there. But I will now go run it at something less than 10.
Yeah, just to comment on Jeff Cargill's question, the paper you may be remembering was written by a fellow named Hughes in the 70s, arguing that there might be thermal convection in the polar ice sheets, but it's not happening. We have radar data across Antarctica and Greenland and drill cores in the high plateau like Vostok. It's layers all the way down.
You sure it's not turtles?
Just out of curiosity, do you also have estimates of the thermal flux, like the actual heat flux from the pipe and the entire region in between? Do you have values for those numbers for this model?
Brilliant. I can get them easily. I
Might-
just didn't do it.
Okay, might be interesting to know.
Yeah, it's really easy to integrate across the top of the model.
Cool.
So I'm trying to understand, are these heat pipes liquid filled? I mean, in effect, are you assuming
In
that they would?
effect.
Okay,
yeah.
so a 1 meter wide liquid filled crack going 100 kilometers, you used the word that it was narrow. That's not narrow if you've been to, which I'm sure you have, many basaltic volcanism provinces. I mean, fissure volcanoes are pretty narrow, and the entire flux from this system is the order of low hundreds of kilos a second. So first of all, I'd urge you to think thinner than that,
Right.
if you want liquid filled cracks. The second thing is that what was referred to the heat flux through the system. If you've got cracks that thin, you lose a lot of the internal heat of the liquid that's rising through the system. And one of the challenges we have is the amount of heat that you lose can cause complete freezing if you don't set up your system right. I would really try to couple your liquid filled heat pipes with this thermal model and see what the effects would be on a hypothetical liquid going through that crack, because I think you'll run into some quite strong feedbacks.
Actually, it's not as bad as you might think. I have got a couple of them set up to couple that, just because numerically it's not that difficult with COMSOL. The actual thickness doesn't matter so much as the mass flow rate.
Yep.
So obviously, for the physics
Which
to
is
come
very
out,
low.
right? Mass flow rate. All right. The heat pipe effect, which gives you the warming of the walls, ameliorates substantially the freezing as you get thinner and thinner cracks. Just because as you let them run, the walls warm up. They certainly don't melt, but they keep the pipe warm, which makes for a very stable situation. So I think the freezing effects have possibly been overestimated.